Okay, let's take a start. All right. Okay, hopefully it's recording. Okay. All right. So, okay. So far we've what we did last week. We did with control volume. All right. So I hope you are quite familiar with what that is by now. All right. So next we do, and we did mass continuity. Okay, from here. Now you want to do this one, momentum. All right, so analyze problems, momentum problems with control volume. All right, so mass continuity, we had for the system, we have mass conserver. So dm on dt equals to 0. All right, the mass doesn't change for a system, doesn't get heavier, doesn't get lighter. For the control volume, we had d on dt integral rho dv. All right, so this is mass of the system, rho times the volume added up. So we have to change that, plus rho rho v dot n dA. All right, integral equals to 0. This is integrate across the volume. All right, so sum up across the volume. This one sum up across the area. All right, so v is a vector, dot n is a vector. So v dot n automatically accounts for what's going out, positive. So this one is rate of change of mass in CV. This one plus, all right, mass, rate of mass leaving minus rate of mass entering equals to 0. All right. So in other words, if your rate of mass is leaving is positive, all right, then this should be negative. Then this positive balances out with this negative, give you 0. In other words, if your mass is leaving, then your control volume is getting lighter. This should be negative. Is that okay? If mass is entering, then this will be a negative. This has some value. Mass entering, so this will be positive. Positive minus this one will give you 0. Is that okay? So it always balances out. Anything going in, all right, your mass, your rate of mass, your change in control volume is a positive. Anything leaving, your rate of change of mass will be a negative to balance out so that it's 0. Is that okay? Okay, huh? It's balanced. All right. Now for momentum system, this one is sum of forces is equal to mass times acceleration. So remember the difference here, this one you can see already. We don't have to worry about the direction one. Okay, this one we have to worry about direction. This is a vector. Mass is not a vector, mass is a scalar. A is a vector, A got direction. All right, or if you like, you can say sum of forces in the x. Don't worry, this unit all Cartesian one, no cylindrical, no polar, all that kind of weird coordinate system. Okay, A in the x. All right, so that's x direction, x, y, and z. And you can do for the same also for the others. All right, sum of forces in the y equals to mass times acceleration in the y. I think you can figure out what the z one looks like now. Okay or not? All right. It's okay, huh? You seen before F equals ma, huh? Maybe somehow can avoided the whole thing you didn't see before. Is it possible? Take chemistry instead of physics for year 12. And then first year don't take dynamics. Can, right? Don't take physics. Statics not F equal MA, what? Alright? Anyone did that way? Alright? Okay, I don't know. Maybe some, I don't know. Alright? So, this one control volume. Actually, this is, can I say it actually more this way, equals to rate of change of momentum in the control volume. Okay? This is actually what it is. Alright? The way the second law, Newton's second law was written, actually, sum of forces is the rate of change of momentum. mv is the momentum. Okay? Mass times the velocity. That's the momentum. Okay? But normally, if you do the chain rule, now I think I cannot escape. All must have done chain rule. Alright? dm over dt v plus m dv over dt. So normally this one's 0, so you don't have to worry about it. Okay? But in our control volume, well, you know, in our system is this one will always be 0, but in our control volume, we need to track what's going in, what's coming out, and so forth. Okay, so same, except here not 0, but same. Let's see, look. This, the only difference between this and this is add a v here. Right? Mass, you just take m. Momentum is mv. Okay? So just add a v. What happens if you just add a v? Okay. I take this one, I copy, so that I don't make any mistakes. And I paste here. Can drag. Right? This is one of the things you can do on here, you can't do on whiteboard. Alright? Okay? Alright? So, I add a velocity. Right? Rho. Alright? This is actually rate of change of momentum in control volume. Alright? So as long as the momentum, as long as nothing goes in or out of the control volume, then actually that is all. You don't need to worry about this. Okay? But that's not the case. In our control volume, sometimes some part of the system might leave, some part of the system might enter the control volume. That's why you have this term here. Right? Not. If not, this is actually, we will have stopped here. But unfortunately, there's some leaving and some entering. So again, we multiply by V, dA. Alright? So this would encounter equals to sum of the forces. Right? Previously, force is also a vector. So previously, for the system, you just have to worry about the force, and you have to worry about the change in momentum. Okay, this is sum of forces, is MA. Well, M, rho dV, that's the M times volume, velocity, MV. Rho dV is M, multiplied velocity, MV, and the rate of change of that. Is that okay so far? So, this one is sum of forces. Forces on control volume. Alright? External forces are normally. Okay? So this one is same. Momentum. Again, this rho V dot N will make sure we the positive, the leaving is positive and entering is negative. So rate of, instead of mass multiplied by velocity, rate of momentum. Leaving minus rate of momentum. Okay. V dot, yeah, correct, entering. It's correct, is it? Alright. Just also rate of mass leaving. So M is the normal vector pointing outwards. So V dot N is the velocity component, that is the component of the velocity that's leaving, not the component of the velocity that's tangential. That one doesn't leave. Okay? And that multiplied by the velocity vector. Okay? So this one, V dot N becomes a scalar. This scalar multiplied by this vector. Okay? So this is a vector, this is the vector, and this is the vector. The other parts are all scalar. Is that okay? So this vector must line up with this vector, must line up with this vector.